Let's do an example where the Taylor series isn't centered at 0. Here at the top is the Taylor series for e to the x centered at x equals 1. This time, let's use a second-degree Taylor polynomial to approximate our values. So the second-degree Taylor polynomial is these first three terms. The remainder on that polynomial is all of the rest of them. So again, the question is, what's the error? This time, let's say that x is going to be between 0 and 2. 0 and 2. So a pretty small interval around the center. The question is, if x is guaranteed to be in that interval, what's the maximum the error could possibly be? So let's write the error term for r sub 2. I know it should be the third derivative, because the n value here is 2. So the third derivative evaluated at some number c, divided by 3 factorial, times x minus 1 cubed. And again, if we want this error, if we want to guarantee that the error is smaller than this value, we have to think about what is an x value in this interval and what is a c value that would make this error term as large as possible. So in the interval from 0 to 2, it seems like a value of 2 is going to make this term as large as possible. And again, we have to figure out what's the third derivative of our function. So I'll rewrite this. Our function is still really easy to find the derivative. It's still just e to the x. So the third derivative is e to the x. Evaluated at c is e to the c. So if I plug in numbers that will maximize this, I'm going to plug in x equals 2. And I know c is between 1 and the x value, because it's between the center and the x value. So I think, again, if I plug in 2 for c, that's going to maximize the error term. So I'll plug in 2 as the maximum value for c. I'll plug in 2 as the maximum value for x. So this whole term just becomes 1. And so now that this error term is large as possible, I know that my error is guaranteed to be smaller than that. Let's do an example where if we want our error to be a certain size, we'll figure out how many terms do we need in our Taylor polynomial if our approximation is going to be good enough. So let's say that x is going to definitely be between 0 and 2. And we want to force our error term to be less than 1/100th, say. Let's write the general error term. So I know that the error associated with the nth degree Taylor polynomial is going to be the n plus first derivative evaluated at c over the n plus first factorial times x minus the center to the n plus first power. So let's write what we know. I want the absolute value of this error to be smaller than a certain amount. The absolute value, because depending on what x is and what c is, maybe the error could be positive, maybe the error could be negative. But either way, I want the absolute value of all of this. I want the absolute value of all of this to be smaller than some small amount, like 1/100. All right, so the question is, what value of n will make this happen? Well, first, let's figure out, depending on what x is and what c is, what's going to make this as large as possible, because we want to consider what's the worst possible case before we figure out how many terms do we need. So in the worst possible case, I think x is going to be 2, because that will maximize this. This nth derivative, this n plus first derivative, is the same thing it was in the last examples. So we've got e to the c over n plus 1 factorial times x minus 1 to the n plus 1. So again, if we want to maximize this expression, I think x should be 2, and I think c should be 2. So we've got now e squared over n plus 1 factorial. When x is 2, this whole term just becomes 1. So I want this to be less than 1/100. Well, I can drop the absolute value sign now because I know n is definitely going to be positive, which means this whole expression is going to be positive. So let me just reorganize the terms a little bit. I'll multiply by 100. I'll multiply this by that factorial. So I've got 100e squared is less than n plus 1 factorial. Okay, you don't have a good analytic way to figure out what value of n makes this inequality true, but it doesn't take very much experimenting with your calculator to figure out that you can just plug in a couple of values and just test to see when will this expression actually be larger than that one. And that will tell you how many terms you need in your series.